Good morning, all of you. In the last class of our Bayesian classification, we have studied minimizing the average risk. So that's what we have been analyzing in the previous class. And then we have also considered some special cases of it, where, for instance, this is the expression that we obtain when you are going to deal with two classes and your prayer probabilities for those two classes are equal, and the lambda I is becoming that means in your penalty matrix the diagonal elements are 0. So this is what we have looked at. uh, so in summary, there are at least two things that we have looked at in the last couple of classes. One is, how do you make a classification when your objective is to minimize the total probability error that you are going to commit? So that's the first thing we have looked at. Second thing we have looked at is how do you perform a classification when your objective is to minimize the average risk? We are calling it as minimizing the risk because there are instances, as we discussed in the preceding classes, that uh, like misclassifying a a sample characterized by a given feature vector from 1 to 2 may be more riskier than misclassifying a feature vector that belongs to 2 to 1. Okay, that's where we are giving some penalty weights and then we are looking at it. So these are the things that we have discussed so far. And let's solve one example now, which essentially would look into this minimization of total probability error as well as total error probability, as well as minimizing the average risk. Okay, please also work along with me in your notebooks. So for this example, let's consider your let's say two class problem we would consider, right? There are two classes. Also consider the prayer probabilities are equal. P of omega 1 equal to probability of omega 2. Then what should be that value? If they are equal, there are two classes. So what will be that value?
Half.
Half, correct. Then another thing let's do is, uh, you need the likelihood function is required, correct? So you have probability of, how do you get the likelihood function? X bar given omega 1 is one thing. Another one is probability of X bar given omega 2. So I should also tell you what is the length of the feature vector. Let us consider the length of the feature vector is equal to 1. There is only one element in your feature vector, so that for drawing and all, this would become easier. And these distributions we have to say. So let us assume that these are Gaussian distributions with, let's say, the variances of both the distributions are equal. Let the distribution sigma square here. So let's take this as 1 by 2. And here also sigma, let me call it as sigma 1 square here, sigma 2 square here, 1 by 2. Okay. Then let's consider this mu 1. This is centered at 0. Okay. The mean is at 0. For this mu 2, you consider this is centered at 1. Okay. Now, let the first one that we are going to calculate be compute the what could you call that, a decision plane. Compute the decision plane that minimizes the total, minimizes total error probability. Okay, probability error, or however you call. So you have here, good thing is just one x is there. Okay, x bar, I'll just write it as x. Now let's call this, let this be 0 at x equal to 0. The initial one is at, the likelihood function is at centered at 0, and with 1 by 2, let's this be 0. Another one is at second mean is at 1, so somewhere let's call it here. Okay, and a variance of half is there for both of them, so maybe something like this. Okay, I'm not plotting it exactly, but that's okay. Then the second one is centered at 1. Since the variance is same, it will be of same magnitude at the peak, is it not? Because the area under them the same, except that there is a translation of that with change of mean. So I have plotted it very badly here. Okay. Yeah, they should have been same. So please, you draw it better than me. You make an improvisation or your teacher there. Okay, that's the same thing which has been moved there. The center is at 1. And if it is computing PE, what is it equivalent to in these graphs? Which one does that correspond to? So decision plane means what is it that you have to find out for which x value? This x is varying here. For which x value, if you consider as the decision plane, such that before that value you assign it to omega. Let's, this is now, if you
You're
want me to
talking
write,
about x naught.
correct, x naught. What is the x naught here?
0.5, sir.
X. Yeah, very good. That's true. But in terms of graphs, how do you find out where it is? If I give you two graphs.
Sir, the intersection point of both.
That's right. That's right. Good. And this is probability of x bar given omega 1. See, this is a very simple thing. Even without doing any calculation, you could say that, because you are simply translating it and putting it at 1. So obviously it would be in the middle. So easy to say it, but again, all problems will not be so simple. So let us do this problem, take this problem and figure out how to solve it also. So the intersection point will give you the decision plane, which would tell you your x naught, if you call it x naught, that is equal to 1 by 2 here. But how do you compute that in practice? What is the what is where will you be having that line? How do you know that? Probability of x bar given omega 1. Okay, ideally, if you want, I could also write probability of into probability of omega 1 should be equal to probability of x bar given omega 2 into probability of omega 2. Is it not? Or you could bring everything to one side and then make it to 0. Anyways, here the prayer probabilities are same. So how could I write that? X naught corresponds to that value for which your probability of, I'm even dropping that bar there because it's a one-dimensional one, x given omega 1 minus probability of x given omega 2 is equal to 0. You tell me the equation for probability of x given omega 1. It's a Gaussian with mu equal to 0, sigma square equal to 1 by 2. Right? Now you tell me, what is the equation for a Gaussian here? 1D Gaussian. 1 over? Hope
Root
it
2
is
pi
not over.
sigma square e to the
Right.
power
Root
x minus
2
mu upon sigma
integral
square.
over root 2 pi.
Sigma
Sigma square, if I bring outside the square root, what would be that? It's just a
sigma
sigma, right? What is its value? Sigma value is
1 by root 2.
right. So let me write it in the numerator, root 2 there. Okay. And exponential of minus of what
X
would I
minus
get
mu.
inside?
X
Then
minus
what
mu
is that?
whole
What is that value now? X minus mu whole square is?
x squares.
Right. X square divided by, then
Sigma
what?
sigma square.
Is it sigma square or 2 sigma square?
2 sigma square.
Right. 2 sigma square means how much is that value?
1.
What
1.
is 1? So this is simply x. So this root 2 and root 2 gets cancelled. So all I am left with here is 1 over root pi exponential of minus x square. That's the distribution here. Correct? Hope everybody is with me till here. So let's please do the same thing here and tell me what is it that you get here. If the earlier steps are clear, you should be able to do it well before me. 1 over, please work yourself. Root 2 pi. Again, this sigma is same for both. So root 2 exponential of minus of x minus. My mu here is 1. So I would get minus 1 whole square divided by, again 2 sigma square is 1. So I just simply have it. So that is equal to root 2 gets cancelled. 1 over root pi exponential of minus of x minus 1 whole square. Correct? So these should be equal here. So that when they are equal, that will give me the value of x naught for which both are equal, or the value where these two are intersecting. So how do I get that now? Let that x be x naught there, okay, for which it is doing. So 1 over root pi into exponential of minus x naught square is equal to 1 over root pi into exponential of minus of x naught minus 1 whole square. And its constants is the easiest thing to get rid of. Then what? How do I solve this then? How do you solve this when you have exponentials? What do you do?
Take logs.
Right. Taking log to the base e on both sides. Very good. That's what you should do. So on the left hand side, you have minus x naught square is equal to minus x naught minus 1 whole square, which is equal to minus x naught square minus 1 plus 2x naught. These two get cancelled. That implies x naught is equal to 0.5. So that is giving you the plane where it is, if x, that means you have given an x, for example, so that if x is less than x naught, which is equal to here 0.5, that implies you will assign x to omega 1, else if it is greater, you would assign it to omega 2. Clear, right? So this is what we have done now for minimizing the total error probability. Is everybody with me, and is it clear to everyone? Or any questions here? So let's now work out another example now for the same distribution, but I have a penalty matrix, or I'll call it as a loss matrix, right? We're calling it as a loss matrix. Now it's a 2D one. So this would be of 2 cross 2. Why is it 2 cross 2? Because there are two classes. So it's a 2 cross 2. What does that typically have it? Lambda 1, 1, lambda 1, 2, lambda 2, 1, lambda 2, 2, which means, for example, lambda 1, 1 is, you should, it actually belongs to class 1. You assigned it to class 1 only. Obviously, that penalty you will give is 0. Similarly, lambda 2, 2 for the same reason is 0. Now let's keep lambda 1, 2 to be 0.5, lambda 2, 1 to be 1. What does that mean? If a sample belongs to class 1, but you have wrongly assigned it to class 2, you are going to penalize it by a weight of 0.5. And on the other hand, if your sample actually belongs to class 2, but you have assigned to class 1, then you would penalize it by a weighting factor of 1. Right? So again, let us consider this earlier ones of tumors that we are considering: malignant tumor and benign tumor, for example. If these are the two classifications that you are doing, which one do you assign to which one would have been which class if this is your last matrix? Okay, probably will the benign tumor be class 1 or class 2? To which
Class one,
class
sir.
it would have? Very good, very good. Omega, this would have been omega 1 and this would have been omega 2. Otherwise, if the other way around, you would prefer a weights of 0, 1, 0.50. Because look at here, a benign tumor falsely or wrongly classifying into a malignant tumor is acceptable. That means benign tumor classifying it wrongly as malignant tumor would correspond to lambda 1, 2, that is 0.5. Now a malignant tumor, that means it is actually omega 2, falsely classified as benign tumor, that is omega 1. That means 2 wrongly classified to 1 is more. So that's how you should want it in practice. Anyways, that's hope the physical interpretation of that is clear to you. Now with that, now you compute x naught now for this. Where will it be? So this is clear to you now here, how it is there here, which has been there at 0.5. And how do you compute that? You have this equation here. We worked out in the previous class. Let me put the same equation there. Just to avoid the time of writing this equation, I am pasting it here. Okay. Now, what is this one? Probability of x naught given omega 1. Do I have it, the expression for it already? Yes, I do. This is the equation 1 by root 2 pi into exponential of minus x square. Again, I'll copy paste that here just to save some time. That's equivalent to lambda 2 by lambda 2 1 by lambda 1 2. What is that value now? Lambda 2 1 by lambda 1 2. What is that value? How much is that?
2, sir.
2. Correct. So 2 times, maybe exponential this at least I will write. So again, I of course have 1 over root pi there also. We worked it, this we worked out earlier, right? It is root pi here, exponential of minus of x minus mu. Your x minus mu is 1. This is what you have it, correct? So now you need to, this would give you x naught. You will get when you equate these two now. That's what would give you the x naught. Okay. 1 over root pi, 1 over root pi. After that, how do you solve it now? This is the way to solve this.
Same applying log on
Same
both
thing.
sides.
Right. Apply or take, so taking now log to the base e, or you simply write ln on both sides. What do you get by that? So what is there on the left hand side? What are you going to get because of that?
Minus
Minus
x square.
let's call it x naught square
Yeah, x
equal
naught.
to yeah. What do you write? What do you get here?
ln 2 plus
Very good.
and
ln2 plus
minus of x naught 1 x naught minus 1 whole square.
I will just put minus here.
Okay.
Straight away. Minus of
X naught minus 1 whole square.
minus 1 whole square, right? This is what I need to solve. Now ln2 minus x naught square minus 1 minus 2x naught. This and this would cancel out. Now I'll take x naught to the left side. That will give me 2x naught. In fact, I'll just bring the 2 this side. That will give me this. And then what am I getting here? So 2x0 equal to natural logarithm of 2 minus 1. Hope that expression is correct. Or did I make any sign? What is natural logarithm of 2?
0.7. So it is
Did I
approximately.
make any sign mistake here? I made a mistake in that equation. Can anybody point it out? There is something wrong I have written.
1 minus ln2.
Yes, because can you correct what is the here I have written minus. This is in fact plus, correct? So this I would get minus 1 by 2 here. Okay. So that's equal to 1 minus what is ln2? I made a note somewhere, but I forgot.
0.7.
What is that? 0.7, huh? Okay, something like that. Okay, so I remember the last answer, it will be 0.153. Something like this you would be getting, right? 0.3 and then 0.15, just one more decimal. So your x0 is 0.153. Let's again just validate that from this graph here, which we have plotted. This is 0.5. This has moved to somewhere here. Maybe I'll draw it with a different color. So this is your x0 now for this case. And obviously, which is your, if you consider this benign and malignant, this is a malignant tumor. And this is a benign tumor. Correct? So what is going to happen now? This probability till it is smaller. So this obviously would move in this direction here. Because even this is small error until it becomes too small, you would like to do. That's why it has the boundary compared to the earlier one has moved to the left. Is that clear?
So this matrix L, sir, which we are
Hmm.
taking 2 by 2,
Right.
it is fixed or
You tell me what will be the size of the matrix, this last matrix in general. You mean the elements, values of these elements you are talking, or size of the matrix you are talking?
sir, I'm talking about the size, sir, not the L.
Right. You tell me what would be the size of this matrix. Anyone can tell me what would be the size of, what is it that decides the size of this matrix?
The number of classes.
Right. So tell me, I tell you that number of classes are m. Now tell me what is the size of this matrix.
M cross M.
M cross M.
Very good. Very good. Very good. Now it tells you, see, because for each class, this matrix has to tell, if I put it into some other class, what is the penalty that I am going to impose? If there are m classes, first row will tell you, if I classify 1 to 1, of course, 0, 1 to 2, 1 to 3, I misclassify that which belongs to 1 to 4. And finally, it actually belongs to 1, but I classified as m, so that is lambda 1m. Same thing I do for each class, right? So the size of this matrix is m cross m. Good question. Is that clear to everyone then? Is that answering your question?
Yes, sir.
Now, let me point out a couple of more things, small things before we go into another relatively bigger topic. So one thing is decision surfaces. I would call it as decision surfaces. See, the way they are calculating so far is that you are essentially computing. If you see even this example that we have worked out so far, we are essentially computing the decision surface. This, your feature vector being one-dimensional, here you got a line. If your feature vector has two components, you would have got a surface. If it is for more than two, you still get a decision. You would perhaps call it as a decision hyperplane, or typically people call it as decision surface in L-dimensional space. Surface there, they use it not in the context of 2D. Typically, one way is we usually use surface to 2D, but they call it decision surface in higher dimensional space, or you could L-dimensional surface. That way you could put it. You don't want to misuse or abuse the word surface. You could say L-dimensional hyperplane, you can call it. Once you have it, you will be able to know to which class it belongs. For example, let us just simply look at this first, minimizing the total error probabilities. So there, what is your decision surface? If I call it as g of x, assuming that I have two classes, is probability of x bar given omega omega 2 minus probability of x bar given omega 1. What does that mean? Let me again write here, entertaining you with my graphs. Okay, again, assume whatever I draw, they are Gaussians. Okay, right. So this is what you would be getting. What would be its value here on this decision surface? What would be the g of x bar value? G of x bar value on the decision surface will be, I take, this is my x bar. Okay, just you imagine this in 1D, you can nicely extend it. As I said, they will be just hyperplanes. So what will be the g of x bar here?
0, sir.
0. What about this region? This whole region, if we call it as R1, so what will be the g of x bar value here in terms of its sign? Of course, the
Oh.
value would vary, but what would be
Positive.
that value? Negative.
Positive. Why
Negative
negative,
or
sir?
negative? Because
Negative, negative. Yes, sir. Omega 1 is
this
yes.
is more correct on this side. So again, assume here that both the Gaussians have same mean. What happens if they are of different mean? We will come to that in the upcoming classes. For now, you assume that as you move on here, you go away towards the 0 or minus infinity, your first Gaussian is having more value than the second Gaussian, which will not be always the case. If you have with varying variance or standard deviation values, that will come a little later. And now what about this region R2? If I call it, g of x bar will be positive, on this side positive. So what you are essentially finding out here is a decision surface. So at this point of time, let me also clarify you or add one more point to what we discussed earlier about the generalizing the risk function. Let me go there and give you a clarification there. If you recollect, it is this equation 10. Maybe I will just copy paste this here and keep it in our current one. This was the equation that we have obtained earlier there. So you could notice here, this is integral over Ri. What would you be doing there is you can interpret this equation in two ways. One way is essentially there, you are going to compute the regions for each of them. Computing regions is equivalent to computing the decision hyperplanes, is what you are going to compute. While you are in a training phase, that means you are finding out the regions. How do you do that? You fit the decision planes such that a given sample belongs to a right class. That's how you would be doing it. So that's how you would be during the training phase, you would be computing the decision planes. And of course, once the decision planes are there, during the test phase, you would see when this is going to get minimized. So I'm making this clarification because that time I was mentioning you only one side of the story where the training has been done. And to compute this, you would simply see which is giving you a minimum value. If you recollect, I have written this L as Li. You compute, you assign it when Li is less than Lj. For all j that is not equal to I, then you assign it to the ith class. That means At that time, you already know the regions of it, but that is not true during the training phase. And what you would be doing, but on the other hand, during the training phase, you know already the classes to which each sample belongs. During that, and then you do not know the boundaries. But when it comes to the testing phase, you do not know to which class it belongs to, but by the time you should have already figured out the boundaries. So this is one thing. And again, we will finding out these boundaries right away based on this Bayesian framework is not always a simple thing. This is pretty complicated in such some scenarios, and will give you a limited freedom on including new constraints or modeling new things into your system. So people do it in a slightly different way. So that is there where there is something referred to as discriminant functions. They are referred to as discriminant functions. So notice here, for computing this decision planes, what all you have to do for the training phase, you need to model the prior probabilities. You need to model or get a model or get the parameters of that model. That is what I mean to get a model of it. Mu and variance for each of the classes you have to calculate. Then you need to evolve, maybe when each one comes where this decision boundary should go based on your last function, you have to figure out and eventually arrive at that. Instead of that, what they will do is a deviation or a slight uh, or a slight deviation from this whole process of actually computing and having a base in always in the probability is a diversion from that is taken, and people calculate them based on some function on them. Okay, say for example, let's say your gi of x, gi is defined gi of, maybe still let me keep it as x bar here, which is probability of omega I given x bar. Then what people would be, or no, you apply a function on your likelihoods. Let this function be monotonically increasing function. Just pay your attention here, something new we are discussing here. It is just an introduction to this. Anyway, we'll come back to it after we complete the current module. We will come back to it. But before I switch on, this is the right place to at least mention about it, because we are doing till now and what we will be doing to the rest of this module is a probabilistic Bayesian approach. But later we are going to, in the coming modules, we'll take a diversion from there and a different path from there, for which we just mentioned that background here. Assume that you have a monotonically increasing function f. This is what is this function f? You will define it later. And then what would happen if, for example, this f of probability of omega I given x bar, you could compute it, and f of probability of omega j given x bar, you could compute it. Each of them, this is a function for which an input is x, that some input, just to avoid f of y, you call it. Obviously, these two, when omega j of x and these two are equal, right? Of course, then if you define something called as gi of x minus gj of x, what is this gi and gj? Let me call this as gi of x bar, and this as gj of x bar is this. This is 0 at boundary, and this G, let me simply call this function also. I don't want to write everything like this. So let me call Gij of X bar as this. So this Gij of X bar is negative, right? Negative. If this is negative, means this X bar belongs to omega 1. If this Gij of X bar is positive, that means this X bar belongs to omega 2. Pay attention here. This is not a difficult one. Just you need to get comfortable with this notation. That is all it is there. I'll again take you to this hyperplane here. Look what is happening here. Probability of X bar given omega on the, just consider it for a simple minimizing total error probability. Okay. That case you consider. When both are equal, it is 0 here. That's exactly is this condition. But now what you are doing, instead of computing on the probabilities, you are applying a function on it, which you are some f of that. But this is a monotonically increasing function. So if your probability of omega I given X bar is more than probability of omega j given X bar, obviously Gi of X will be more than Gj of X bar. So if this difference is positive, the difference of G functions which are taken on it will also be positive, and vice versa. So instead of directly computing the probabilities, you would use a functions on that. Why a function? You would gradually realize that. We will come to that a little later. But at this point, it is sufficient if you understand that if there is a monotonically increasing function applied on these likelihoods, still this positive, negative, zero boundary you could do on this function instead of doing it on the likelihoods or likelihood multiplied by your prior probabilities. All I am doing is, earlier, based on the differences in the likelihood functions, I am making a decision. Now, I am using the values of these likelihoods as an input to a function that takes one value. This is the value I would give it as an input. And this function is monotonically increasing. That means if x1 is greater than x2, f of x1 will be also greater than f of x2. If x1 is equal to x2, f of x1 is equal to f of x2. And similar, the case is less than also. So since this relative thing is maintained, and if I am going to make a decision based on whether the difference is 0, positive or negative, I could make the same inference based on now the difference of these function after applying, giving this probability as an input to a function and difference of these functions. That's all. So as we will be now dealing with the Gaussian things, so let's spend some time and ensure that how do you represent a Gaussian in at least 1D and 2D, and any generalization, how do you do that? This analysis we are going to do. So let us first get comfortability with the Gaussian distribution. That's what now we'll do, Gaussian distributions. I'm sure most of you would already know by this time, but we will ensure that all of us are in the same page, even if you have not remember from your earlier courses this Gaussian distribution well. So let's start with 1D Gaussian distribution. Okay, so let me call it as G of, or maybe let us use a capital letter this for this distribution. This Gaussian, anyway, we'll write it capital. So you have two parameters, mu comma sigma. How do you write this function? G of mu comma sigma, how do you write that? 1 over. How do you write this function? Or let us, given that mu and sigma, let us write it as a probability density function. Okay, this Gaussian, you could use it as a probability density function. P of x bar I am writing, although Right now I am considering a 1D, one-dimensional feature vector. So how do I write with mu and sigma 1D probability density function? Help me with that. P of x bar equal to 1 over
1
Root
by
2
square
pi.
root of 2 pi
root 2 pi.
sigma square
Yeah,
exponent.
I'll just put it outside. I will just simply write sigma. If I'm putting under square root, I should have written a square, but I would write it like this into exponential of minus of x minus mu whole square into divided by, what do I get in the denominator?
2 sigma square.
2 sigma square, right? This is the distribution. Now, I give you a distribution now. Listen to me carefully. I give you a distribution now. And so in this case, by the way, mu and sigma here is being 1D, P of x bar, this being 1, these are one-dimensional ones, right? How do I compute mu value? How can I compute that? I have given you graphically P of x bar. Then how do you compute mean for it? This we have in fact worked out already in the histogram equalization, but slightly in a different form. So you tell me now, how do you compute mu here? I have given, is it clear? I have given you a graph
Peak value.
of P of x bar. I have given you, okay, this is my x bar. This is my P of x bar. I told you that it follows a Gaussian distribution. Give me the values of mean and variance. How do you compute mean?
Integral.
So integration over
Hmm.
minus infinity to infinity.
Then what?
X bar.
Okay, I'll just write x because this is 1D.
P of
X
x bar.
into,
P of x bar probability.
okay. Then
P of x dx.
that's all. If I give you a distribution and if you need to compute the mean value, all you do is integrate it from minus infinity to plus infinity. You write how much is this x value here, or how many are taking this value. Of course, then the normalization is there in P of x bar as the area under that is 1. Okay, x into P of x into dx. And this you would represent it as another thing is there. This is the expectation value of x. That's how you write it. I'm sure you would have come across this in one of the communication related courses or statistics or probability related courses, is it not? Now, then I follow it with the next question. How are you going to compute the variance of this in similar lines? You first tell me in terms of this expected value, how can I write it for variance, for computing the variance? What
X
is
minus
the
mu. X minus mu also. Variance from
very
mean.
good, very good, very good. Correct. X minus mu.
Whole square.
Correct. Because I am not talking about standard deviation, but about variance. This interpretation is pretty simple. From every value, you are subtracting the mean, and then what is that expected value of this variance? That this expected value of this would give you the variance. Since you are looking at not standard had it been standard deviation would have been different. You are looking at square, so this will be x minus mu whole square. Now you know that this is the definition for expected value of x. Now based on that, now you tell me what is the how could I rewrite this in terms of an integral there, minus infinity to plus infinity. You tell me what do I get to compute sigma square here?
X minus mu
Hmm.
whole square
Hmm.
into P of x dx.
Very good, very good. In place of x, I have x minus mu whole square. So you just keep there x here. Okay. Anyway, this probability for that particular one is probability of x into dx. This would give you the variance value. Okay. Anyway, you know how to draw them for 0, 1. What will happen? You already know it. Okay. Even the plotted some things here. In this example also, we have plotted some beautiful sketches of that. Okay, hopefully, if not me, would have plotted them better there. Okay, so in the next class, we would continue our discussions on that.